Hi, everyone. So my name is Sophia. Today we're announcing a secret project. Before I do, thank you for the warm backstory. I did have a lot of luck and worked on a lot of really cool things. One of the things that I worked on for the last few years was actually teaching Rust professionally. And a lot of us have been using Rust. Okay, I want to get a kind of a show of hands. How many people feel really comfortable in Rust? Raise your hands. Okay. And then drop your hand. Now, you're allowed to drop your hands if you've been working in Rust for less than a year. Oh, look around. Okay, that's how long it takes. So in teaching Rust, one of the things, yeah, you can your hands down. In teaching Rust, one of the things that I noticed is watching people's faces when you're teaching Rust for the first time. Some of you who've been teaching Rust have seen this look. You start explaining one concept, you're like, hold on, hold that thought, and you start teaching another concept, hold that thought, you teach another concept. And eventually it starts to click, but it takes a long time for things to click. So I started thinking, can we bring safe systems programming to a larger audience? So here's the secret project. Here's our secret question we want to answer. Is it possible to bring safe systems language that's easy to read, easy to teach, and easy to learn? Is this even possible? Does it have to have the complexity of Rust to be a safe systems language? So, introducing a new project called June. I've been working on this project for the last year and a half to try to answer this question. So here's our goal. We want that readability, we want that teachability. In fact, during the last few years, I've been talking to a lot of friends in the industry, and some of the people I've been talking to are Go developers, and I was like, is it even possible? This sounds wild. Is it even possible to have a safe system language you can learn in a weekend like you can with Go? We also wanted the having the ability to teach quickly or to learn quickly. We pair that with being able to maintain it as well. So we're not giving up too much. We want a code base that grows, and as it grows, we're not accruing a lot of technical debt. As well, as you can imagine, I spent a lot of time working on Rust, a lot of blood, sweat, and tears, as we say, and I want Rust to continue to grow and thrive in the areas where it's great. And I think that this can be kind of a sister language to Rust. For the things that Rust doesn't focus on, we can focus on. The kind of focus areas of Rust and embedded and like high performance systems, that's great. But what about application development? We can have a design of a language that fits well for application development with a bit of a systems flavor. As they sit together, they cooperate. So that's the kind of thing that we've been thinking about. Okay, review. I'm sure everyone is looking at this slide going, what the heck? That's not quite Rust. So what are we missing? Lifetimes. Not just lifetimes, but say louder.
Semicolon.
What? Okay. There's some syntax. Well, okay. So when we say lifetimes, what two things do we mean when we say lifetimes? Yeah, we've got parameters and annotations, right? So if we stick those in, okay, yeah, you and your semicolons and commas. Okay, so this is starting to look a little better. But if you think about this from the perspective of what do you have to teach to understand what you're looking at? When I started working in Rust, it took me months to understand this because, as we think about it, there's about 5, give or take, different concepts that work together. And as they work together, you begin to understand what you're looking at. We have the concept, the general concept of lifetimes, then annotations, parameters, the general concept of ownership and borrowing, and how that goes with the ampersand, and of course, generics. So not only do we have lifetime parameters, they're part of the larger generic system, and you have to understand the relationship. It's quite complicated, but it's quite precise. It's one of Rust's core strengths, is to be able to have this kind of memory precision. So the question is, what happens if we don't have this kind of precision? If we loosen it just a little bit, what happens? So that was one of the questions I wanted to ask, because I know that if you want this kind of precision, you get this kind of complexity. Okay, so this is what we're going to do. We're going to think in groups of related allocations specifically. If we make a linked list, so we've got a 3-node linked list here. If we thought of this as separate lifetimes, where each piece of memory has a separate lifetime, this can get pretty complicated to encode in our lifetime system in the kind of bar checker. But if we think about all of these as having a single lifetime, imagine a pointer pointing to the head. That single pointer could have a single lifetime, and everything that you reach to that pointer could share that lifetime. Has some interesting trade-offs, but has some really interesting benefits. So let's talk about the benefits. Before we talk about the benefits, though, I have to show you some code so that we can build up seeing these benefits. So let's see some June code. Here's our first piece of June code. How many people can read this? That was quick. All right, so we're readable so far. That's good. We'll check in later about that. So we've got our struct, and we're creating a new employee. And that new keyword is handling an allocation and construction, just like it would in something like Java. For us, in this language, we actually don't have a borrow checker, but we do check the lifetimes of things. And in fact, we infer the lifetimes of things. So here we're going to start inferring the lifetimes of the pointers that you're creating. New employee is going to create an employee pointer. And to understand the lifetimes of that pointer, we start asking questions. Because all the lifetimes come from a group of related allocations, we kind of collapse the idea of lifetimes as something very simple. Does this pointer escape the function? Yes or no? No. So we have a very simple name for this lifetime called local. No tick A or tick B, just local. All right, see another example. Slightly bigger. Raise your hand if you can read it. All right, okay. It's warming up. Okay, good. All right, so in this example, we're a little bit more complicated. We have our instantiation of our employee, then we pass it to setStats, and setStats updates the employee with the new stats object. And so our question now is, what is the lifetime of the pointer, the new stats age 33? Well, does it escape the function? Yeah, how does it escape the function? Through employee, through the parameter. We'll call that param employee. So it turns out there are 3 different ways that you can escape the function, or you can not escape the function. You can escape through a parameter, or you can escape through a return value. And those are 3 different lifetime names that are very readable, that we can kind of present in error messages, and we can teach very easily. Okay, there is a bug in this code. Raise your hand if you can see this bug. Ooh, it's subtle. 1 person. I'm very excited. Anyone else? Okay. I mentioned that allocations are grouped. So if an allocation is grouped, it lives as 1 and is freed as 1. What happens to new stats age 22? It kind of leaks, yeah, but it doesn't leak in a traditional sense. A traditional leak, the memory is gone and you can never reclaim it. In this sense, you can kind of think of it as a memory bloat, quote unquote, in that it's part of the group and it's just going to stick around until the group is finished. So that's going to be part of our trade-off that we'll have to address as we develop this idea further. And we'll talk about some of the ways that we'll address it. So keep that in mind. Okay. Now let's have some more fun. Linked lists. Raise your hand if you can read this one. Yes. Pretty straightforward, right? It feels kind of like Java, where, something lightweight, something garbage collected. So we create our linked list, we just set it up, and we're done. All the lifetimes congeal, coagulate, what's a good word? Collect into a single lifetime. And that gives us the flexibility to do this. We make a circular linked list just as easily as we made a singular linked list. Raise your hand if you want to write that in Rust. I thought so. Yeah. So having that single lifetime simplifies the lifetime system down to the ability that we can make any arbitrary data structure we want as easily as possible. Obviously, like I said, there are trade-offs, but these benefits are plentiful. Okay, on we go. Let's take a pause. I just made a circular linked list. What rule did I just break? Think in Rust. If I have references, what am I allowed to do? I can have. Well, it's circular, yes. But if I have references, if I have two mutable references to the same thing, is that okay? No. Why? What did I just do? Yeah, see? Aliasing, mutable aliasing. What did I just cheat on here?
I didn't mean to sell.
Well, it's not actually that. They are real pointers. Yeah, I've been to rule. So I have a mutable pointer and another kind of like another pointer pointing the same thing. We've got an alias. That would not be allowed in Rust. So let's take a second and think about it. See if I have a slide for that. Yeah. Before you do, let's do a little quiz. Why? Let's do two mutable pointers pointing to the same thing. Why is this bad? Yeah, that's the big one. If I have that same thing copied twice, put one on each thread, and I write at the same time, there we go. So clearly we need to protect ourselves against that. So what are we going to do? Just like Rust, these kinds of shared pointers are not allowed to be sent between threads. Okay, now we're down to single-threaded, two mutable pointers, or one mutable pointer, one immutable pointer pointing the same thing on a single thread. What happens now? Well, you get some tricky situations. Yeah, I see you back there, Nico. So one of the big ones that you're going to get is kind of spooky action at a distance. That's what you might call it. So I write to something in this area of the code way over here, and I observe it way over here. And it's difficult to debug, right? So we need some solution to that as well as classic things like iterator invalidation. Okay. So one way we can think about it is we need to kind of isolate ourselves when we have these kind of shared pointers. You can kind of think of the graph. If this helps your visualization, great. If it doesn't, fine. But you can kind of think of this interrelationship of owners and pointers. They're kind of pointing onto each other, and there could even be like more complicated relationships, like some pointer pointing to some faraway place. What we need to do is to discipline this graph of relationships that are happening in your program. One way we can do that is through, like I mentioned, isolation, by kind of cordoning off the group of related shared pointers from everything else. If we can prove that they're fully isolated, then the kind of spooky action at a distance disappears. And we have a set of clear ownership patterns. And then in little fenced in areas, we get to bend the rules a little bit more because there's a discipline to it. Okay. So what does this look like in code? There happens to be something that we can use from object orientation to get this kind of isolation. Encapsulation. So if we go back to traditional encapsulation, being able to say that information is hidden from, or I should say the implementation information is hidden from the rest of the world, we can say, all those shared pointers are stuck inside of the class, and that doesn't leak out. In fact, let's tighten encapsulation even a little bit more. If we do that, we can enforce that no pointers go in and no pointers go out that can create aliases to the inside that class. Okay, once we do that, now we can have that full graph isolation we were talking about. Okay, so in code, this is not scary. I don't know if we'll actually use traditional classes like OO. We'll talk about that here in a second. But the idea holds. We've got a class, we've got a private data, we have the ability to kind of create new of these circular lists. We can create a nice API around this, and we can prove that nothing is aliasing into this or out of this. This gives us some really cool properties. One of them is, if we have an instantiation of this class, we can make that a single owner instantiation, right? Once it's single owner, we can send that between threads. We've just given ourselves thread safety and the ability to create any arbitrary data structure we want. Because of encapsulation, we can create a clean API, just like we can with, traditional classes and whatnot. We've got all private data, and then we can create our set of methods and a clean way into working with it. I mentioned before that this does have some trade-offs. So we saw the flexibility. We can make arbitrary data structures. We can kind of isolate them. But we saw the memory problem from earlier. How do we fix that? So one of the things that encapsulation lets us do is to fix it, is to say, here's a set of pointers that we want to track and then we want to work with and potentially recycle. So let's talk about that. The traditional way of working with memory like this, if I have all of this memory that's going to live together and then die together, I can't just pick a little piece of it out and free it, right? Just like you have like an arena style allocation, you have like everything lives and dies together. But instead, we can use a classic technique like free lists. We can take that piece of memory and then put it in the free list. And if we need some memory later, we can just pop it out of the free list and use it. But the problem with free lists is that they're not safe. If I accidentally put something on the free list that has an alias somewhere else, that's not okay. So what we need to know is if we have multiple copies of that same pointer, if we do, then we don't allow you to recycle it. Okay? So we need to build this into the language. You'll be able to annotate a class. You'll be able to track all the pointers in that class. And then when you want to recycle one of them, you can say recycle that pointer. And it will only allow you to recycle it if that's the last copy of that pointer. Does that make sense? Everyone's kind of staring at me. Yes? Okay. So we have a kind of balance here. By having a flexible system that groups allocations, we have the ability to describe, like I said, any arbitrary data structure. The code is very easy to read, easy to use. And having been using it the last few weeks, I can tell you it is actually quite a joy to write in because you never have to think about anything. And then when you need to tighten your memory up, you can use this safe memory recycling technique to say, okay, here's a node. I'll recycle this node, and then I'll reuse that memory later. Okay. So I kind of touched on some of these. These are some of the things that are coming up. There's going to be a recycle keyword. It's not automatic because it's a linear time operation. But yeah, this gives us that safe memory recycling. All right. So there's a lot of work that we're going to be doing. We have a reference compiler that we're going to release later today. And in that, most of what's in this talk is already implemented, except for the safe memory recycling. That will be coming in the coming weeks. We also want to add better abstractions. I kind of mentioned classes. I didn't want to talk about the experiments that we're doing, but we want something that's like object orientation, but is even easier, even more composable, even more modular. So that's another thing that we'll be working on. As a sister language to Rust, one of the things that's really, really important to us is to be able to interop this language with Rust, we want something like the Rust stable ABI to be in place so that June is not isolated from the rest of the world. That June can connect to not only to like C-based APIs, but also Rust ones, connect to the Crate ecosystem and to be part of kind of the greater kind of Rust or safe systems ecosystem. So we're definitely looking forward to kind of collaborating on ways that we can do that. And finally, there's quite a lot of new techniques that are coming up in working with memory in a safe way. The creator of Veil recently put together a list, and there's something like 14 kind of unexplored memory safety techniques, in addition to, say, the borrow checker, that we're very much looking forward to kind of continuing this exploration. So you can kind of think of June not as something that we're trying to ship today as a 1.0, but it's like opening the conversation about how do we make safe systems programming open to a much larger audience, and then continuing to kind of grow that over time. Okay, so here's some of my socials. The GitHub repo is not yet public. That will be public soon, and there's going to be a blog post very soon that comes after this talk. That's going to go live. That will go into a little bit more detail and give you a little bit more of a place to jump in if you're interested. Okay, any questions?
Thanks, Sophia. That was great. Are there any questions about this? See one of here. Is there an overlap between Rye and June?
So Rye and Truffle, which was another one that was secretly released about a week ago, are embedded in Rust itself. This is completely a standalone language with its own compiler and everything.
And it's not going to be interpreted, it's going to be fully batched.
There may be a REPL at some point. People that have been following my new shell work know I'm quite a fan.
All right, in the back there.
You mentioned a Rust interop. How do you do that without a stable Rust ABI?
You can't, unfortunately. So we would have to emit Rust and play inside of Rust's way of thinking about the world, which is considerably different than the June one. We did play with that idea initially, but I think the path forward requires Rust stable ABI. Something like Avanyo's work would be chef kiss perfect for this kind of interop.
Thank you.
And this one over here.
So when you're talking about safe linked list, you're talking about kind of an encapsulated set of pointers where the pointers weren't allowed to escape. And I was wondering how you would then iterate over that list, because in Rust you would maybe call iter and you'd again get a reference to each item. But if the references can't escape, then how do you do that?
Yeah, there's a couple of ways that we're playing with. I'm not sure exactly what's going to become the quote unquote, June standard way of doing it. We're playing with the idea of generators. So being able to pass in a block that runs, and then the container can safely run it over the elements. There will likely be a kind of borrow as well. That's very limited. So you can ask the container, hey, I would like the item at this location, and it lets you borrow it in a very kind of local scope that doesn't escape into a struct or get returned, whatever. So we will have some limitations like that that will allow you to access and iterate.
I mean, some of you're inferring many properties to allow the lifetimes to be as you shown. Couldn't you instead have that implemented in Rust itself?
You can't, because it's just exceedingly different to what Rust does. There is a package, though the name of it's escaping me, that gives you some amount of that. But part of the tricky issue with Rust is that the Rust learning curve is immediately going to hit people. They have to learn some amount of Rust. And with June, we just remove all of that. We go straight to having a simplified memory model for the grouped allocations. And that's really the big win at that point.
Just a quick question: How do you write the compiler? I mean, which language do you use to write the compiler?
It's not self-hosted yet, but I'm sure at some point it might be. It's all in Rust currently.
In the first example you gave of working with the employee record, you passed that to a function, modified it, and then looked at it in the caller. And it looked like there weren't any sigils on the parameter type. So it seems like you're by default passing by reference and allowing that to be mutable.
Oh yeah, I guess I
You can pass by value if you want to.
Yeah, so I kind of breezed over this. It's kind of hard to introduce the language and all the little nuance all at the same time, but this actually brings up a really important point. Everything that you're creating in June is a pointer. Every pointer has a lifetime. So every bit of user-defined data is always a pointer. If I pass that pointer to a function, it's a pointer to that function. The function says the binding is mutable or not. If it is mutable, it's a mutable pointer. So that's one of the things that keeps it easier to read, is that we remove this the differentiation between reference and value and whatnot. It's just all pointers.
So what do you do in June if you want a type that has value semantics, like something that feels like a number, for example? Like I can pass it, I'm passing a copy, not passing the original.
There is currently no way to do that. We have enums and pattern matching, though I don't show them here. And we may at some time have a record-y kind of thing. But one of the things that we're trying to do, like we did with NewShell, is start with the basics that we think can bear the most weight, can kind of carry us forward the best, and then only add the things that we need as we absolutely need them to keep us as kind of streamlined as possible.
Hi, so thank you for your talk. It was great.
Thank you.
And I had a question because one of the big draws of Rust, at least to me, is the very elegant way of error handling. And I was wondering what that looks like in June.
That's one of our favorite questions. It's currently being designed. So Jay, my collaborator, is sitting right behind you. And we are both, as you can imagine, exceedingly passionate about errors. Since I created the compiler errors and she worked on error and some of the important machinery for error reporting for users. So these are conversations Jane can tell you ad nauseum that we've been exploring and we'll continue to explore because we want this to be top-notch.
There's a question online. What about lists and iteration? What about lists that are iterated and updated while in iteration? Is that something you support, and how would you do that?
Yeah, so the iteration story we were talking about before is still kind of in progress. We want to kind of pick the right balance of features so that as it lands, it can kind of do more work than just kind of simply iteration. Sure, whichever's next.
All right. I think that concludes the questions. You've answered them all well.
Right.
All right, give a big applause to Sophia.